Hey, yo, what's up, guys? Baby Bear 4812 coming at you one more time with another cheeky tree problem. Today, it's problem number 333, largest BST subtree. If 666 represents hell, then this question is definitely halfway there. I'm being dramatic. It's not that bad. Facebook likes this one as of recent. Decent acceptance to submission ratio. And overall, it's a pretty good problem. It's a pretty good problem. And in this problem, we're told that we are given the root of a binary tree, and we need to find the largest subtree, which also happens to be a binary search tree, or BST, where the largest means it has the largest number of nodes. So just to be clear, the tree itself that we're given does not need to be a BST. It's a standard binary tree, but we're looking for the largest binary search tree. As a reminder, though I'm sure many of you are familiar by now, a binary search tree is a tree in which all the nodes follow a couple of properties. The first one being is that everything in the left subtree is less than the value of the parent, or the root, and everything to the right is greater than the parent. Subtree must include all of its descendants, excuse me. The follow-up says, can we figure out how to solve it in O of n time complexity? The answer is yes, we can, and that's what we are going to do. If we take a look at this tree over here, this tree alone is not a binary search tree. The reason it's not is because if we notice the root 10, so everything to the left of the 10 is smaller, but everything to the right is not larger. Namely, this 7 over here is a tricky little bugger because he shouldn't be there. If this was a binary search tree, it would be on the other side. We maybe had the 7 where the 8 is, and then the 8 would branch down off one this way. But them's the breaks. So how do we figure out what the largest BST is? So a couple of things, actually. You can think about breaking this problem down into two separate problems. One problem is, can we determine if a tree is a binary search tree? Shameless plug, I'll leave a link to that video down below. If you don't know how to solve that problem already, I would suggest checking it out first. I think it'll make this problem a lot more sensible. And I take a very similar approach, so there's some nice overlap there. The other problem is a much more trivial one, which is to say how many nodes are in a binary tree. So what you could do as a brute force solution, this would be an O of n squared, time solution, would be to say, let me check every possible subtree to see if it is a binary search tree. And as I'm checking all of them, I would say, let me keep track of what the size is of this tree that I'm looking for. And if it's a binary search tree, I could just return the size, and if I kind of go from bigger to smaller, then the first one I find will be the result. Or we can take the approach like we're going to do, where we're going to keep almost like a global result variable that we're going to update as we find BSTs, and then return that at the end. However, we could do this in linear time, so in using one walkthrough, and that's what we're going to do. So again, brute force I mentioned, we're not going to be implementing it. It's always good to mention that one in your interview, but we can definitely do one better without twisting our brains too much. It does require getting a bit clever though, so hang on tight, but I think we can make it happen. And already we're like 2 minutes in, I'm already blocking the view. That should be better. Alright, so we said that the brute force solution was checking if every single one of these items was a binary search tree. So we can check this whole tree, and then we check this tree, and then we check this subtree, and this one, and this one, and this one. That would be n squared time. Is there a way for us to do this though in linear time? Again, the answer is yes. I think I've already let the cat out of the bag there. The method we're going to use is we're going to start traversing the tree from the left subtree onward. So I guess we'll do like a post order traversal. Hypothetically, you could also do it from the right side, but I think left side, so starting from the left and going downwards, kind of having this as almost our starting point, if you will. We're going to recursively go down here toward the bottom left. And what we'll do is like I said, in kind of a post-order fashion, like check the left root, check the right root, and then see if this parent will conform to those rules. And so, namely, let me maybe be a bit more specific. We could see that this right here is a binary search tree. The reason this is a binary search tree is because all the values here on the left are subtrees. So 1, just a node itself with no children, is a subtree, or is a binary search tree. 8 is also a binary search tree. 5 is a binary search tree because both of its children are binary search trees, and everything to the right of it is greater than 5. Everything to the left of it is less than 5. And in fact, I should have mentioned this. In this example, that's the answer. 518 is the answer. And we would output 3 because the largest binary search tree is of size 3 within this entire binary tree. So let's think about this. We're going to do this in a post-order manner, and every time we get to a root node, so we're going to have a terminal condition. So maybe we'll say our terminal condition is going to be, do this. Our terminal condition is going to be if we hit a null node. So if we hit a null node, what do we know about this node? We want to kind of push back a few pieces of information. We're going to want to do the following. We're going to want to return one piece of information, which is going to be, and actually even before I get into the piece of information, let me say the key to doing this in linear time will be to grab multiple pieces of information from one node and then push it up. And once we push it up from the left and right side, when we get to the parent, we're going to have information coming from both children. If we have information from both children, then we're going to be good to go and we can make a decision as to whether or not this is a BST. So as I was saying earlier, one of the things we need to decide on is my left child a binary search tree and is my right child a binary search tree? So first thing I'm going to return is this a BST? Well, if we hit a null node, the answer is yes. A null node is always a binary search tree by default. So imagine we had this condition, this one would kind of check its null children over here. Both of them would return true. And so when we get to this node, then we filled in one of our conditions, which is the fact that we have, how do I put it? That both of our children are subtrees. So maybe, let me write this down. I'll say both. So these are a BST conditions. So I'll say binary search tree conditions. Some brilliant spelling. I'll say children are binary search trees. And I'm going to say left is less than root. And what I mean by that is just shorthand for all the values to the left are smaller than the root. And I'm going to say all the values on the right are bigger than the root. So these are kind of the three conditions. I know they listed 2 here. But it's a bit misleading because for this whole thing to be a BST, both of these also need to be BSTs, okay? So we're going to return that yes, this is a BST. We're also going to want to return what are the potential minimum and maximum values that my parent can take on from here. Namely, what's the minimum value in this left search tree here of these null nodes, and what's the maximum value? Well, the minimum value, I'm going to put my notes because this part I found a bit confusing, and I want to make sure that I kind of cover this properly. So I'm going to go back and repeat what I just said. What we're going to be interested in finding is to make sure that this root 5, for example, think about it this way. If I want to check, I'm comparing my left subtree. I need to make sure that the value at my root is greater. Make sure that I get this right. Again, I got it written down. I need to make sure that the value of my root is greater than the maximum value of my left subtree. So if this is my left subtree, I need to make sure that 5 is greater than the maximum value. If I don't have a maximum value, and similarly, let me say this, 5 needs to be smaller than the minimum value of all these. If I'm returning a null node, what I'm going to want to return by default then for my min value, if you will, is going to be infinity. So I'll draw it like this. And for my max value, it's going to be negative infinity. And let me explain why in just a second, why we're doing that. It'll make more sense when we get into the code. And finally, the last thing I'm going to want to return is going to be the size of the binary tree, so that when we're rolling things upwards, I'm going to be able to keep track of how big this subtree is. The reason I'm going to do this is as follows. Imagine that I get to here, so I get to 1, and I've checked my left tree, I've checked my left child and right child. Both of them have returned this. What I need to make sure is I need to say, is my left, first off, are they both subtrees? You know, is my left child a subtree, is my right a subtree? Yes, they are. They both return true, okay? Now I need to check, is my value here, my root value, greater than the max of the left subtree? The max of the left subtree, so is it bigger than negative infinity? The answer is yes, because we want everything to be bigger than the null node. So whatever we have is by default going to be bigger. That's why we're putting this as our base case here. Similarly, I need to make sure that 1 is greater than everything in my right subtree. So whatever the whatever the minimum value is of this right subtree, whatever the minimum value of this right subtree is, we need to be less than that. Okay, so that minimum value we're going to put as infinity, because no matter what I put in, everything will be less than the 1. Once we propagate upwards and we start pushing up, and now we have a value that we can potentially put in instead of these infinities, we'll deal with that in the code. So then we're going to be making a decision on what value to push upwards. But by default, this is what we're going to be returning for our null condition. Now, imagine I get here and I can acknowledge now and say, okay, I can return this value. I can return, something about this 1. And first off, if I'm going to stick to this format, which I will, I know that I need to return true. So I'm going to need to return the fact that yes, 1 is a proper binary search tree. Okay. I'm going to put in some maximum and minimum values, and then what I'm going to do is I'm going to put in the size of this subtree. So this one is just going to be 1. The way that we got 1 is by saying, remember, so we had, we kind of did 2 checks here for children, neither of which existed. Both of those returned subtrees and binary search trees of size 0. So when we return binary search trees of size 0, we're going to say, well, size of 0 here, plus size of 0 here, plus 1 to include the node itself. So by having 0 plus 0 plus 1, that's how we end up with a tree here of size 1. And when we kind of build this one up, we're going to have some maximum minimum value, and then I'm going to be returning a binary search tree of size 3, because like we said, this is definitely going to be a binary search tree, and this subtree is of size 1. This one's of size 1, and then we have one more here. So left size plus right size plus 1 is going to give us this size. Now, how do we actually push up? Like, what value are we going to be pushing up for the new kind of left minimum the minimum and the maximum values of the subtree that we're going to be using to compare when we get to the parent node? So here's the thing. For my actual minimum amount that I'm going to be pushing in here, if the minimum amount that I previously had was something bogus, like infinity or negative infinity, then I'm going to be pushing up the value of this root itself to 1. Because what I'm going to want to do is say, like, at the very minimum, like on the left-hand side, this is the value that we're going to be pushing in. And same thing with the maximum. Okay? So when I actually get up here, when I get to this 5, I'm going to be asking myself, what's the maximum value of this left subtree? The maximum value is 1. Okay? The minimum value in this case isn't really going to play a part. The reason where the minimum value will play a part is when we're on the right subtree. So when I'm pushing these values up, this is kind of the part that's a bit weird to wrap your head around. I'm pushing these up, and this value, this maximum value, is the one that I'm going to be using if I'm looking at my parent. I've made a call to the left subtree. I'm going to be interested in this value over here. When I do the same trick from the right side, I'm going to be interested in this value over here. And so actually, let me jump on over and say, this is definitely it's a binary search tree, and the minimum maximum value we have are 8, and the size of it is 1. So when I get up here, what am I going to be interested in? I'm going to be interested in saying, let me grab, if the minimum here, if this was we've already determined that this is 1. So when I get up here, I'm going to actually grab the left minimum, which is this value 1 over here. Up here, in this point, I'm going to say if I'm interested in grabbing the right maximum value, then I'm going to take that right maximum value as it is, and that's going to be an 8. All right. So now, what happens when I get to this 10? Since the 10 is going to be pulling all this from the left subtree, we want to know what the maximum value was of this left subtree. The maximum value was 8. So when we do a comparison, the root value is going to have to be greater than that kind of left maximum that we had, and that was this number here, which was 8. So far, as we're going through this, we've just noticed that we have a subtree of size, a binary search tree, of size 3, and that's the best we've done so far. So we're going to update like a global result variable. The reason, again, it worked was because we did this comparison. So we compared the 5 with the maximum value of the left and the 5 with the minimum value of the right. And then since they were both also binary search trees, it by extension was also binary search tree when these two other conditions were fulfilled. If we try to do the same thing backwards this way, we're going to end up returning a false here among other information. And the reason we're going to return a false is because we'll notice that our value here is greater than something on the right side. Since this one returns true and the 5 returns true and the 15 returns false, 10 by default will return false, and we will not actually be taking into account the size of this potential binary search tree because it's not a binary search tree, right? We're not going to be taking it into account because one of its children is false. One of its children is not a BST. Therefore, by default, the 10 also cannot be a BST. So by using this kind of pre-order logic, we're going to build it from the ground up and get to the top. And as we're going, we're going to keep track of the biggest BST that we find. I hope that explanation made sense. Let me know in the comments below if you have, my hair's all lucky, if you have any other questions. I'm happy to elaborate on it. But otherwise, let's kind of jump into the code, or not kind of, let's fully jump into the code. And then I think with the code, it'll kind of make a bit more sense. So we have, let me move my face back down here. I'm going to move this over here. And so what we can start with doing is, so I think all the entries here are going to be valid. So even if we have 0, we're actually going to take care of that in our edge cases within our recursive function. So I'm not worried about any error checking here. As per usual, we're going to be doing some sort of depth first search since we're walking through here. So I'm going to call it depth first search. And the only thing we're going to be passing in there is a root node. So like I'm just leaving that as a placeholder for now. I then said that we need some sort of result variable, which by default will be 0. We're going to want to return the result, but before we do that, we're going to have to make a call to our DFS function. So I'm going to make it on the root, and that's about it. And that's the only call that we're going to make. Thanks for watching the video. No, I'm joking. Obviously, the work comes in here. So the first thing we're going to have to do is the terminal condition on when we're exiting here. So we said we're going to hit the terminal condition if we get a null node. So if not root, what do we want to do? We want to return a few things. We want to return true. We want to return, and we said here, infinity and negative infinity for a minimum and maximum respectively. Float infinity, float negative infinity, and finally a size of 0, because this is a binary search tree. So true denotes the fact that it is a binary search tree and it's of size 0, right? And the maximum value that we need to beat is negative infinity when we get to the parent. And the minimum value that we need to beat under is going to be float of infinity. That's why even though this represents a minimum and this represents a maximum, the values are almost flipped. So maybe, as I'm like recording this, I'm wondering if there was maybe a better verbiage that I could use or nomenclature for the variables to not have that confusion. But I think, again, if we get through this video and if you try to walk through this example by hand at least once on paper, I think that it'll make sense. But again, if you have any feedback, let me know in the comments down below, as always. So since we're doing, like I said, in a post-order traversal, we need to actually make calls to our left and right subtree. So we're going to have to call DFS on root.left, and we're going to have to call DFS on root.right. Now, when we do this, we're going to want to be gathering a certain piece of information. Namely, the piece of information we're going to want to be gathering is all of these items, right? And what I'm going to do is I'm just going to, let me do this. Using a array decomposition or list decomposition, I'm going to almost extract these, so when we get the return values, each of them has their own variable name. So the first one I'm gonna say left is BST. So whether or not the left subtree is a BST, then we're gonna have left minimum, left maximum, and finally we're gonna have left size. So imagine that we make a call to our left subtree and it returns all this information. We're going to know if it's a BST or not, which is a Boolean. We're gonna know the minimum and maximum of that subtree that we need to either beat or come under, and the size of that binary search tree. On the right side, we're going to do the mirror image, except it'll be right instead of left. So we'll say right is BST. Maybe I think this looks a bit better. We'll do right min, right max, and right size. So with object destructuring, we're going to get all of those values. Now, there are two things that can happen. I'm sitting at this root, and now I've gathered all this information that I have recursively about my left and right subtrees. Either now, depending on what information I get, either I am a subtree or I'm not a subtree. And depending on which one of those I am, that'll determine what sort of information I'm going to be returning upwards. And so let's determine first if we are a subtree. So if we're a subtree, that means that our left side is a binary search tree. So that means left is BST is definitely true, and right is BST is also definitely definitely true. We said also that our value, so root.val, has to be greater than the maximum of what we had on the left side, right? So whatever's on the left side must be smaller. So it must be greater than left max, and that the value must be less than the minimum value of the right. So everything on the right is larger than us. We need to be smaller than whatever was on the right side, the minimum of what was on the right side. So root.val has to be less than right min. If all these things are true, then we have a BST. Cool, and we can return whatever, and we're going to talk about what we're going to return. Otherwise, we do not have a BST. Okay, sad face. And so the return statements are going to look slightly different. So maybe we'll do it if we don't have a BST first. I think it'll be just a bit easier. The part before is you're going to have a few extra lines of code. So if we don't have a BST, we're going to want to return false. It's the first bit of information here, whether or not we're a BST. And now the actual minimum maximum values that we need to beat, if you will, aren't going to matter, because whatever's coming, whatever parent from here on outwards is using this branch or this part of the tree, it's not going to be a BST no matter what. So if you think about this over here, any piece of the tree that gets information from here is not going to be a BST by extension, because one of its subtrees is not a BST. So we can kind of just throw in almost like, they're not really dummy values, but we're just going to throw in the same infinity and negative infinity that we had before, because we just need items that are always going to pass these tests. Like if I put none, if I put something like none, then these comparisons wouldn't really work and we'd get errors. So we're just going to put the infinity and negative infinity in there so we can just keep passing these tests. But since we're returning false as, not a binary search tree, for some child, grandchild, great-great-grandchild beneath us, we're always going to be getting false. So we'll never be able to get a bigger binary search tree. And finally, not that this matters, again, we're just going to be passing in a size of 0 because we're saying, well, this isn't part of the binary search tree, so we can't add it on to a bigger sized BST. Now, what if we do have a BST though? Well, we're going to have to return the following, and there'll be a couple of items that go before this, but eventually we're going to want to return true that we do have a BST. We're going to want to return the minimum of the left side, the maximum of the right side, and then the size of this BST. And so the size of this BST will be the size of the left subtree, which is left size, plus the size of the right subtree, which is right size, right? So imagine 1 plus 1 plus the root itself. So plus another 1. That's what we're going to be returning. And so this left min and right max value, we may need to adjust slightly. So we said the following. We said that we might need to push up a different value than the one that we received. And that'll namely happen if we get these infinity values, because we set our terminal condition at a null node. So what I'm going to do is the following. I'm going to say that left min is just going to be equal to the root value that we see if left min currently is equal to float of infinity. Otherwise, if it's not, then I'm just going to pass along left min as it is. The reason I'm doing this is because if we're getting this infinity value as our minimum, like we did from the null nodes, we're never actually going to be getting a valid comparison. And once I get up to this 5, I won't actually be taking into account the fact that this value here was a 1, because I'm always going to want to be kind of making sure I'm not under this infinity value. And again, if you work this out by hand, I promise it'll be a bit more clear. So I'm sorry if I'm not if I haven't really cleared that up thoroughly, but that's the general logic behind it. Same thing with the right max. It's going to equal to the root value if right max is equal to the float of negative infinity. Otherwise, we're just going to leave it as it is. So we'll leave it at right max. One thing that I forgot is actually, if we found a binary search, we need to update our result, right? And so our result at any given point will equal the maximum of the result itself and the size of this new subtree, this new BST, which is going to be left size plus right size we determined plus 1. And since we're trying to modify this variable which exists out here, if you've watched my videos long enough, you'll know that we need to put in a non-local result to make this happen. And this should be it. I'm just going to give a quick run to make sure that I haven't gotten anything perfect. We got like 97 percentile runtime. Wicked. So, all right, let's do a quick recap. We said that to solve this problem, there are two moving parts. One is that we need to determine if a binary tree is a binary search tree. Again, I've linked a video for that down below, and that will explain how to do this. If you watch that video first, then this whole process will make a lot more sense. I promise it will. The other is to say how big is this tree. Seeing how big it is, it's pretty easy. Let me take a step back. Even before I kind of got ahead of myself there. Having those two problems, we can implement a brute force n squared solution, n squared times solution, which will walk us through tracking every possible subtree for being a BST, and we'll grab the size along the way. We said, however, that we could do this in linear time with one walkthrough, but we're going to need to get a bit clever about what information we're passing up as we're propagating upwards back up the tree. Seems to be my new favorite word, propagating. I gotta cut that one out of my vocabulary. So as we're going back upwards, we need to take into account, is what I found so far actually a BST? If it is, cool, we can keep making more BSTs, right? That's how we have this condition here. If we can't, it's not happening, we're always going to return false. These two values, and the size is what we can always pass along and see. If I've found a BST, well, then I'm just going to take the size of my two subtrees, and as long as the value kind of works with respect to what the max and minimum values are of the children, then we're adding one more to that size, and we're updating this global result variable as we go. The part that I think is the trickiest, that took me the longest to wrap my head around, is this relationship between these left min, left max, right min, right max variables, and how they behave with respect to the actual creation of the tree and the conditions under which something is a binary search tree. If the root value is greater than what the maximum of the left side, which is everything is smaller than us there. So if I grab the biggest item on the left, I need to make sure I'm bigger than that item. Whereas if I grab all the items on the right, which should be bigger than me, then the smallest of those, which should still be bigger than me, I need to be smaller than that value. The reason, and almost the counterintuitive piece, when we're passing in this infinity for the minimum value and negative infinity for the maximum value, is when we're coming up from the null node onto our parent node, so from the terminal condition back up, we need to make sure that we are beating that. If we're coming from the left side, we're beating the maximum value, which is negative infinity. We need to make sure we're beating it, and we are. If we're coming from the right side, we need to make sure we're beating the minimum value, which is this one over here. So that's why I think maybe left min, left max, and right min, right max might be a tiny bit misleading, but I couldn't think of better variable names, quite frankly, which, yeah. So you can take that for what it is. I don't know if that says something about me and my variable naming abilities, but for what it's worth, that's the general relationship in how we made this problem work. Again, for like a third time, let me know in the comments below if you have any questions, comments, concerns, anything. Smash the like button, comment, share, subscribe, and I'll see you guys in the next video. Peace.